Now let's take a look at the actual MOS layout and see how large the parasitic capacitance exists. Once we figure out how to avoid large parasitic capacitance, then your circuit can perform better in high frequency. This is a typical most layout. We have a gate and diffusion. It can be either source or drain depending on the current direction. From the top view, we have a gate and the diffusion, source and gate diffusion. For W over L size, we have a W width and L length. So actual length, when you draw the length like this, but in reality the channel length can be shorter than what you actually draw. So there's also overlapping capacitance between the gate and the diffusion, right? And also we have a reverse diode junction capacitance. So this junction capacitance on the left, this is sidewall, this is the bottom junction capacitance. Also on the right hand side, another diffusion has also sidewall junction capacitance that is represented by the CJSW, and also another junction capacitance on the bottom. On the channel side, we don't count the junction capacitance. Most of the junction capacitance coming from the bottom and the sidewall. And definitely we have a gate and channel capacitance, and also channel to the body parasitic capacitance. So once we identified all the capacitance in the physical layout, we can model that in our MOS symbol. So they're almost everywhere. We have every terminal between two terminal has the capacitance, parasitic capacitance, as you can see. What would be the dominant one? Probably the CGS is the most dominant, but in modern CMOS, CDB and CSB is quite similar order. So CGS, approximately CDB, CSB in deep submicron CMOS. So we are seeing this kind of a trend here. So we have to somehow reduce the effect of those parasitic. So for the given size of the gate, W over L, CGS is kind of given by the gate and channel. This cannot be changed for the given size. But for the drain and source diffusion capacitance, there is a way to reduce such capacitance. Suppose we want to draw the W over L size of the MOSFET design. So direct drawing like this, the width is W and length is like this. So if you draw single finger like this, the whole area here, so W times E is the area of the diffusion. Such thing we have 2. The overall area for the source and drain quite large. Let's say if you fold the device into 2, so we draw that this in parallel, so W over L times half, W over L times half. So we draw the half of the size, connect the source and drain, and tie the gate like this. Then it is same as the left hand side electrically. So we are seeing larger W. So we have drawn the W well size in 2 fingers. So this is a single finger drawing, this is double finger drawing. If your size is quite large, then you can split that width into as many small pieces as you want. So overall diffusion here, so for example, if the drain is like this, so drain area will be E times half W. But the previous case, drain capacitance was what? So drain area was E times W. For the source, if this is the source is connected through the metal wire. So E times W, half W times 2, we have 2 of them. So that is approximately similar, E times W. So if you split the drain, so you can reduce the diffusion capacitance on the drain. So we prefer to place this reduced diffusion area on the signal output side, that is on the drain. And also having multiple fingers has another benefit. For example, the poly gate has the finite resistance like this. In high frequency, this resistance will slow down and reduce your bandwidth through this gate resistance and also CGS. So we have for example, have a 1 RG in series resistance. Once we split that onto 2, then half of G and half of RG, half of the RG will present. Then we can increase the bandwidth because the channel capacitance is also reduced by half for each finger. So having appropriate size of the finger is good practice. So you have to figure out how many finger or how large unit device you will use. So once you determine the unit device size, for example, then you expand the number of fingers. When you have a different size of the even larger size of the W is required, then you expand the number of fingers like this, right? Of course, you will require to put via as many as possible. Now let's take a look at a little more complicated case. Even in that case, we can figure out how to minimize the drain capacitance. For example, we have a series connection of the M1 and M2 in cascode, and we have M3 on the right. By looking at that, we can see that M2, source of the M2 and M3 can be shared, right? So draw this, and also drain and source of the M1 and M2 can be shared. So we draw that first, the M2 M3 adjacent. So draw the M2 and M3 adjacent. So here M2, the shared diffusion. This is source, and drain of M3. This is F. This is drain of M2, right? So this drain again shared by M1. So this is shared by M1 transistor. So this is E is the drain of the M1, right? So by having this, we can simplify the wiring and also diffusion area so that we can finally reduce the parasitic capacitance. So here, so F is on the bottom, and node N is on the middle here. We have a connection between gate and the C node, M3 gate, and C node is connected through wire, and the E node we have a contact, so the poly connection like that. So this is basically representing the original circuit. There's a much simpler layout and compact than you just draw directly. I will show some FinFET technology nowadays becoming gaining more uses nowadays. The structure of the FinFET is that it has the vertical structure like this, and then gate is wrapped around the source and drain wall. So we have a source and drain in vertically very narrow wall is there, and then gate is surrounding them. In this case, this source drain, the width of the source drain in FinFET technology is fixed. This is provided by the process, so fixed by process. The way we have a large number of W is that we make this more line. So we place the fin, source and drain. So by controlling number of fin, we can increase the W size. This is a fin. This is from the top view. We have a gate surrounding source and drain. If you rotate 90 degrees, we are having looks like this, and having, if you wanna increase the size, we are adding more fin onto that, right? Like this, and even 3 fin, you are having more onto that, and then extend the gate like this. This is a gate, something like that. So the width of the FinFET technology is controlled by the number of fins that you are drawing, shown in here. We will take a look at the MOSCapacitance for different gate voltage. For example, we drive the certain voltage of the drain voltage and then start increasing gate voltage from 0 to higher. So once the VG is at the 0, then transistor is off, so CGS will be 0. Once the gate voltage is higher than threshold voltage VTH, then the channel underneath the device will start forming. So the capacitance will larger and larger. Once you having quite strongly you invert the channel, then you get the stabilized capacitance. That is given by the two-thirds of the WL times COX and the overlap capacitance. We have a CGS overlap, so we have a channel inversion there. In saturation, we have the channel capacitance and also overlap capacitance. If you increase VD even further higher, then what happened? So gate voltage and drain voltage difference will approach the VTH, then it will get into triode region. So the VGS capacitance, once that becomes a triode region, like this, VGS will, and VGD is VGD also forming the capacitance is split into two. So 2x of those two formed by the CGS and CGD we get the gate capacitance given by the overlap and the channel area. If you look at the CGD only, let's say if the CGD only present once the channel, the transistor is get into diffuse the triode region. Once that go into triode region, we will see the CGD capacitance like this. When this is off, so off capacitance is given by the the overlap capacitance, right? So it will start from, if we consider the overlap capacitance, then the off state will start from the W times C of V capacitance. So once we get into triode region, the capacitance we are seeing looking into the gate is what? CG becomes W, 2 times of the upper equation, that is WL times COX plus 2W COV, right? In triode region. So now once the channel is formed, we can look at the gate and channel as a capacitor. So let's, for example, we tie that the source and drain to same voltage shown like the ground shown here. Then all the channel if you raise your gate voltage bigger than threshold voltage, then your gate capacitance will go rise. Since the source and drain is tied at the same potential, we will see that gate capacitance is same as the CG. CGS is equal to CG here. So this if you increase VG, then the strong inversion happens. So the overall capacitance approach to what? W L COX, right? Plus the two overlap capacitance, right? W CO, right? If you reduce now in different direction, if you move your VGS in the negative voltage, then what will happen? If you bring this gate voltage in negative, then what happen is you are repelling. So this negative charge is attracted on the gate, and the positive charge is attracted. Here, positive charge is a hole. So lots of hole is attracted on the surface, that if that such large hole is there, then that can also move freely. So it becomes another capacitance. So in this case, we are accumulating p-type on the p-type substrate. We are accumulating same type of majority carrier like holes. We are attracting that and accumulating such majority carrier on the surface. In that case, also we are seeing larger capacitance. As you have a larger negative voltage applied, you see that the large capacitance, almost similar to strong inversion capacitance. So in this mode, we are saying that this is accumulation mode capacitance. In the strong inversion, we are saying that this is the inversion mode capacitance. So for the MOSFET in triode, so MOSFET in triode region, we can use that either accumulation mode or inversion mode. But the thing is that in this kind of a strong or accumulation mode, near ground voltage, near VGS is near ground, there is some nonlinear sharp transition of capacitance variation. This kind of thing is result in the signal nonlinearity. For example, you implemented like a capacitance, LC, RC, low pass capacitance. So you're driving your signal onto this low pass filter. If your signal is moving around this operating region, then output the signal will see the pretty constant capacitance. But if your signal is near ground, moving up and down, then it is seeing this kind of a large capacitance variation, so your output will be distorted. So when you use this kind of circuit, this kind of second order effect, the capacitance variation kind of thing is well studied, and you have to make sure your circuit is not affected by such a nonlinear variation, or even though such variation is there, your circuit should not be affected by that nonlinear cap. Okay, in terms of the performance that you're to achieve, you want to achieve that certain performance. Sometimes, like some application like the VCO, the V1, like a voltage controlled capacitor, very linear voltage to voltage controlled capacitor is sometimes required. But in the previous example, conventional MOS device has very large nonlinear variation near zero. To avoid such kind of things, we can implement some this kind of structure, and so the problem started in the first place because the substrate type is different from the channel type and also source drain. So we make a piece of here, and we draw that the annual. Typically annual is used for the PMOS devices. Here annual and this diffusion was P plus, but now we are using N plus. So everything is N type on this, and then put a gate here. Now if you increase the gate voltage VGS from 0 to there, the capacitance variation CEGS is linearly moving because there is a majority carrier already there, electron there. So as you increase the gate voltage, more electron, more majority carrier is attracted and getting more larger capacitance we are seeing. So there's no such kind of channel inversion happens. So from the beginning, from the let's say 0 voltage to a certain voltage in your system, you have a 0 and VDD for your circuit. So within that region, your capacitance will be moving linearly. So you can use this linear control so behavior. So when you have a LC oscillator there, for example LC tank here, if you change the capacitance by voltage, you can change the resonance frequency. So resonance F0 to F0 prime by changing voltage. So this kind of application requires some linearly controlled capacitor. For that case, we call this kind of capacitor the Varactor variable capacitor application. We use this kind of structure. Okay. So this is a source. This we tie that this, and this is the terminal 1 and terminal 2, like this. Okay. So device FT we will see here. So definitely for the device FT is the frequency where the current gain is equal to 1. So if you apply the IG input current, we know that there's a CGS there, and ID will flow. So if we tie that to ground, so bias is not shown here. So we just assume that the transistor is in, assume that that is in saturation. Then voltage around on the gate is the CGS IG, and ID will be what? GM times VGS. So that is CGS. Let's see. Like put it a smaller letter. CGS times IG. So the ID over IG equal to, I'm sorry, so 1 over S times CGS. So ID over IGS is GM over SCGS. So this is the frequency over ID over IG versus frequency. You see that you will see like this kind of straight line. This is just 20 dB per decade slope, and the frequency where the current gain equal to 1 is what? So omega t here, so omega t equal to pi ft, that is what? GM over CGS, right? So at that ft, the current gain is equal to 1. So this is the definition of the ft, so omega t. So to maximize the ft, we have to reduce the CGS and then maximize the GM, transconductance. The small CGS and large GM, that leads us to the maximum current gain frequency. Now the question is, why do we care about this current gain, the maximum current gain? Because this is actually what we can use for voltage amplifier. So above this range, above this frequency, we may not expect a large voltage gain, because the following reason. Suppose we have an amplifier loaded by the RL here. So identical stages. We apply the voltage here, V in, then we will get the V out that is loaded by additional stage that will have the same CGS here. Let's we have a X1 stage and X1 identical stage. We have a CGS here. Since we apply the ideal voltage here, whatever is set up here, it will flow the ID on the first stage output, that is equal to what? So GM times V in. So this current will eventually flow through the CGS at high frequency. So if the RL is going to infinity, then all the current will flows onto ID, will flows onto the CGS here. So if you look at the frequency versus gain AV here, so if the RL at DC, we have how much gain? So GM times RL, voltage gain here, and then given by the certain bandwidth RL times, let's say CGS, 1 over CGS Is 1 over 2 pi, that is the frequency. Let me write down again. 1 over 2 pi RL CGS is the pole. It will go down like this, right? What if we have a larger RL, and if the RL going up and down, the DC gain will changes, right, for different RL, right? And the pole location changes. Let's assume the RL is high enough so it doesn't affect the high frequency midband characteristic. So let's look at the midband characteristic around the omega u fu here, unity gain here. So unity gain, you will see the unity gain at the ft of this transistor. So let's see again, to calculate AV is V out over V in, that is what? So V out loaded by CGS. So V out is what? So here V out is what? So ID minus ID times 1 over S CGS. So my ID is minus GM times V in times 1 over S CGS. So from that equation, we can conclude that V out over V in is minus 1 over GM over 1 over GM over S CGS here. This is actually the voltage gain. So if you look at the here, this is like omega T over S. So here Fu is Ft, same as the device's Ft. For this kind of cascaded amplifier structure, the maximum achievable voltage gain is set by the Ft here. So as you can see, the having higher Ft device is very important to have a larger gain at high frequency. As we have shown that the Ft is defined by the GM, over 2 pi CGS, it is important to have a small CGS and largest GM for largest Ft. So according to the device equation, we can drive that the CGS is what, 2/3 of the WL times COX, and GM is what, mu n, GM is what, so approximately, if the n is equal to 1, then what, then mu n COX, this is the mu n COX W over L, and overdrive voltage here, we overdrive, this is the overdrive, like this. So putting that into this Ft, so this is 1 and 2, so this is the final Ft becomes like this. So n is approximately 1 here. So as you can see, to maximize Ft, we want the L, minimum L, so we want to reduce the L. So for large Ft, for large Ft, so reduce the L, and also overdrive voltage to or lower or higher. We want that to higher overdrive voltage. Actually, if you have a high overdrive voltage, then you are working your transistor at the large current level. So ID versus, as you can imagine, VGS. If you have a larger overdrive voltage, this is VTH. So this is the overdrive voltage. So if you are working on the large overdrive, then you are flowing large current. So in that way, current efficiency, I mean the GM efficiency, GM over ID is poor, but is low, but the FT goes up, right? So there's just some trade-off between large overdrive versus low overdrive. For large overdrive voltage, we can get the large GM, mean the higher FT. So we design the transistor, bias the transistor at high overdrive voltage if you care about the high speed. You want to apply the larger overdrive. And also channel length, we want that to be smaller, small channel length for high speed. But if you care about the gain itself, this and also GM efficiency, and then we put overdrive voltage appropriate strong inversion voltage around like 0.2, even lower overdrive voltage, and higher channel length that lead us the large RO, right? That lead us large DC gain. So DC characteristic and AC characteristic, high speed gain and low speed gain, the DC gain, low frequency gain, and high frequency gains are a little different. So if you care, depending on your application, you have to choose your right overdrive voltage and right size of the channel length, right? Let's also take a quick comparison between MOS transistor and bipolar. For the input current, for MOSFET device, there's no input current at bias, but the bipolar transistor that requires non-zero input current, that is IB, the base current is required, that is not zero. And input resistance is infinity because the MOSFET is capacitive input, right? When the CGS is present there. But for the bipolar, we have a diode structure between the base and emitter. So we have R pi and also RB on the diffusion area. From base, finite base resistor is there. So total DC resistance we are seeing like this. And VDS set for MOSFET, certain limit, voltage limit that require VD set, that is the MOSFET in VGS minus VTH. So the overdrive voltage is the required VD set voltage to make the transistor in current operating region. So we have a VDS, so VD set. As long as VDS is greater than VD set, then the MOSFET works as the voltage control the current source. Similarly, the bipolar transistor require certain VD set, that is few kT over Q, that is approximately like a 0.2 volt. So this is fixed. Unlike the MOSFET device, the bipolar, it has the fixed VD set, certain limit set, the limit, the active region and saturation region boundary is fixed for BJT, but MOSFET is changing for different VGS level. So it is following scale law device. So VG set changes like that overdrive. And also GM efficiency, looking at the GM over I, in weak inversion, 1 over certain time, n times kT over Q. Strong inversion, we have a 2 over overdrive voltage. And velocity saturation region, that is 1 over the overdrive voltage. But the bipolar case, no matter what the case it is, just 1 over kT over Q. So only the current level sets the GM. For noise, we haven't looked at the noise yet for the device. I will just recapture. So we had learned in undergraduate course that where we have the thermal noise voltage can be modeled, that is 4 kT. So this is noise voltage is modeled on the input side. So noise spectral density power is 4 kT. This is a spectral density. So 4 kT 2/3 over GM. This is a typical noise equation. But if you include the gate resistance, then we also have 4 kT times Rg. Gate resistance also becomes the noise source. But for the bipolar, we have only 1/2 for the first factor. Similarly, we can define the bipolar transistor noise is similarly defined, but the actual magnitude is lower than the MOSFET device, right? And also we have a base resistance, also noise source. Device offset is for the similar size. MOSFET is 10x larger, and also flicker noise is also 10x larger than the bipolar case. So but nowadays the MOSFET, although this one for the same amount of current, bipolar is faster because it has larger GM and smaller noise and etc. But because of the digital operation, so MOSFET is easier for digital implementation. Like it can operate in digital as a digital switch better than the BJT, because the BJT requires non-zero current onto the base. This prevent us from using this BJT as a switch, because that one flows some current, requires some current for logic operation. But for the MOSFET device, even though this is the switch the device, it doesn't require any static current. Once that switch is finally settled, the output, it only loads the capacitive load only. So once the voltage on the output is settled, then no more current is flowing. There's no DC current onto the gate. But for the bipolar, there's non-zero DC current. So there's a finite DC current need to also flows all the time. That's kind of a limitation. So nowadays, the MOSFET device, MOS transistor is widely used in both in digital and analog circuit. So this is good for SoC design, like require integration. Very large scale integration is easier using MOSFET transistor. This is another graphical comparison for again for the MOSFET. We have a VD set modulated by the overdrive voltage, similar to V overdrive, but for the BJT, VCE set is fixed around the 0.2 volt. Also GM efficiency looking at here, so we have a 4x better GM efficiency in BJT compared to CMOS, but CMOS has the variety of the choice for the GM efficiency. If you drive your transistor into sub-threshold region or weak inversion, then we can get the better GM efficiency, but in return it gets us a slower device size, a slower device speed. Okay. For maximum FT, you wanna have a maximize the GM, and also that increase the current, so that make the GM efficiency poor. So this point is like a lower efficiency point is used for high speed, for high FT device, right? So very important. So for the MOSFET, it's critical. So biasing, how you bias your MOSFET device actually determines your device characteristic. Biasing is critical for MOSFET. In this slide, we will see some difference in between. We will see the difference between the transconductance and R-on in triode region. So we know that the ID in triode region is mu n cox WL VGS minus VTH times VDS minus half VDS square. So we can approximate WL times VGS minus VTH times VDS if VDS is small. Approach to 0. Then we know that the ID VD R-on equivalent resistance R-on is what ID over VDS over ID, that is 1 over mu n cox WL VGS minus VTH. If you look at this equation, isn't that similar to the GM? It's exactly same as the GM of the transconductance in saturation region. So VGS minus VTH in saturation. So we can see the relationship between GM and R-on. For example, we know that if the device is in the saturation, this is the saturation region, for example, and the triode. If the device is in the saturation, each GM is defined by the equation, right? This equation 2. But for the triode region, its resistance, that is, so its resistance, so 1 over R-on here, R-on is same as the transconductance we would see in saturation, right? So we have the relationship for the same device and bias. If this device is, let's say, is in the saturation, then we get the GM transconductance and its output resistance. So here is RO. The slope of that is RO, right? 1 over RO in saturation, and we have the GM of this guy. But that is once that the device is pushed onto the triode by having a small VDS less than V overdrive voltage, then it becomes the resistance becomes same as the GM that we would see in the saturation region, right? So this is 1 over G. The slope of that guy, slope of this R-on is what? The GM then. right? Slope, right? Because that one is 1 over r on, over r on. So this is quite strange. It's quite at the first place, it might look like a weird relationship, but this is a property of from the square law device model that we are using, right? But you should not confuse that in triode region the GM on the transconductance we may see on the triode region is not the same as in the we would see in the saturation region, right? So this is not the actual. So in this triode region we don't have enough GM, so we don't have enough GM, so meaning GM is not GM, right, in triode region. Okay. So if we want to use our device in the triode region and try to, then we make it as a switch. So finite our own resistance and VDS must be less than V overdrive voltage there, right? As you can see from the MOS device, R on is defined by 1 over mu n COX W over L V overdrive. So if the current flows from left to the right, our gate overdrive voltage VTH plus overdrive, we care about this side of voltage. If there is any signal fluctuation going up and down here, right, up and down, so we are kind of modulating overdrive voltage, meaning the resistance we see may different. So R on is in here. Let's say Vx. Let's say the VDS is just so small, so here is Vx and this is Vx minus VDS, right? So in triode region, and Vx and y are similar. In that case, we can draw the on resistance through the MOS. MOS, because this is VDD, for example, at the maximum voltage. If the Vx is 0, then we may see the maximum available overdrive voltage. In here, on resistance will be what? So 1 over mu n COX W over L times maximum overdrive is VDD minus VTH, right? The minimum, largest overdrive voltage we will see, so we will get the small resistance. But if we drive that higher voltage for the Vx, then overdrive voltage going down, so the actual resistance value will move like this. Where is the limit? The limit is VDD minus VTH. Once the voltage on the Vx is greater than this level, then device will turn off. So it will have actually very sharp rise in the on resistance. So this is from the NMOS. What about the PMOS device? Similarly, so we have to make this one as a switch, so we may apply the 0 volt on the gate. That is worst case, the lowest voltage available here. So this is Vy is equal to almost close to Vx. In that case, the on resistance from the PMOS is that when the Vx is VDD, then we get the lowest resistance. That would be 1 over mu p cox W over L overdrive voltage, that is VDD minus VTH. Right? That would be maximum the overdrive voltage that you may see from the PMOS device. So it will now, if we reduce the Vx voltage, then the resistance will go rise until VTH of the PMOS guy. So as you can see, the resistance from the MOS and PMOS are not totally linear for the bias voltage. That we're operating voltage on the source and drain actually determines the actual on resistance. So having single transistor for analog resistance is not good idea, because a very nonlinear resistance we are seeing out of the transistor. If you really want, then you may use wanna use the parallel connection of the PMOS and MOS, like this, so that we can see this RP and Rn characteristics so in parallel. So we see this kind of if we draw that characteristic overlapping the resistance characteristic in here, then we see the PMOS resistance will be like this, right? So if you make it in parallel, then overall resistance will be like that, right? This kind of curve you may expect. So actually between this and that, we'll see the lower one will dominate, so its actual resistance we may see like this, right? So it will may see more linearized, flat Rn resistance we may see, right? Rp parallel Rn. It's getting better, right? So when you wanna have a linear resistor over wide operating range, then you need to use both PMOS and MOS in parallel. But here still it got improved, but this is also still non-linear resistor. Still non-linear resistor. So resistor in CMOS, how we amplifier or whatever analog circuit, how we can implement the resistor then. So typically linear resistor is implemented, so not by the transistor. We use the metal resistor or poly resistor. Metal is just metal line. For the poly resistor that we are using for the poly gate, so first the MOSFET layout, we draw the source and drain diffusion, right? And then draw the gate, right? This is made out of a polysilicon. So if we put more doping onto that, so we can use that poly for the poly. We call it poly resistor. They can be used. There's a BIA on there. So this layer exactly same as the gate of the gate material that used in MOSFET. If you wanna control the resistance, then there's just process control there, where the doping of the polysilicon is controlled. That would define the amount of resistance for different kinds of resistor. So poly resistor has two types: silicited resistor, silicited poly, or non-silicited poly. For silicited, we have a that is typically used in most gate device, because that would reduce the poly resistor, right? If you want to have a larger resistor value, then we use non-silicited poly that would not add doping, too much doping onto the polysilicon, that will create a large resistor. Okay, so there are two different kinds of the poly in process, so that would give us the resistor implementation. So these are the mostly widely used resistor. Another resistor material you can think of is that the well resistor. So you know that in transistor P plus PMOS device, we use the N-well, right? N-well for the PMOS. So this N-well structure can be used for just draw the N-well, then utilize that as the resistor. But this kind of this other N-well or diffusion, anything like that, would have a large variation over temperature. The resistance value is large, variation is large over temperature. So typically we don't use the N-well resistor or diffusion resistor. So mostly in the circuit we use the poly resistor. So poly resistor is most widely used. And also sometimes if you want to have a very low resistance value, you may use the metal resistor, but that depends on. Nowadays, FinFET technology, FinFET use in some of the process, they provide metal resistor, like in FinFET process, but mostly the metal resistor has a very small resistance. So for circuit designer, we may not prefer to use that. We usually use the poly resistor that has the variety of the selection, so the process supports many different kinds of the poly resistor that give us some freedom to choose, and yeah.